Modern cosmology operates under the Lambda CDM standard model. This framework treats the universe as an expanding, flat coordinate grid. This model relies on invisible placeholders to account for 95% of the universe's total mass energy. Our understanding of these distant structures depends entirely on light emitted billions of years ago. Standard measurements assume this light travels across the vacuum without being affected by macroscopic potential gradients. These dark components may be an optical illusion, the result of viewing the cosmos through an uncorrected gravitational lens. If the light path itself is distorted, the underlying structure of our cosmic map requires a total reassessment. The mathematical oversight centers on the background metric. Standard analysis typically sets the time-time component, g sub 00, to approximately -1 along the entire line of sight. In reality, photons traverse a temporal gradient. As they move toward an observer, they climb through a field of decreasing vacuum energy density. The cosmological lensing effect addresses this by treating the macroscopic density gradient directly as a relativistic refractive medium. This framework is governed by a single scalar variable, the velocity potential v sub 0 of r. Replacing a static background with a refractive continuum shifts the study of the large-scale universe from particle physics to classical optics. We define v sub 0 of r as the classical escape velocity of the vacuum relative to the observer's location. This potential embeds directly into the Schwarzschild metric. Substituting v sub 0 squared for the gravitational potential tracks how geometry affects spacetime. Setting the line element to 0 isolates the photon's path, revealing the coordinate speed of light. This geometric solution yields the exact refractive index, n of r. Because the velocity potential v0 has a real value, the refractive index is strictly greater than 1 inside the cosmic potential well. This confirms that the universe functions as an optical medium with a gradient index. Signals from the early universe follow these refractive laws, which redefines our calculation of spatial distance. Current models only apply lensing transversely, treating it as localized noise when light passes near a massive object. Refractive cosmology introduces a longitudinal constraint, applying the optical metric along the entire line of sight. Fermat's principle dictates that light following an index greater than 1 will experience a continuous Shapiro delay. A Shapiro delay is the slowing of a light signal as it moves through a gravitational potential. This refractive drag causes the apparent optical distance to lengthen beyond the true geometric distance. This path lengthening accounts for the dimming of type Ia supernovae, the evidence currently used to suggest the universe is accelerating. This chart shows Pantheon plus supernovae residuals. The upward curve of gray points represents the anomaly attributed to dark energy. Applying the refractive correction yields the theoretical solid blue prediction. In the bottom panel, the corrected blue residuals flatten to 0 across all redshifts. The magnitude anomaly vanishes, fully explained by the optical path lengthening of the vacuum. Dark energy emerges as an observational artifact, the geometric drag of a longitudinal cosmic lens. If the longitudinal index explains dark energy, the same framework must be applied transversely to the problem of dark matter. Standard analysis uses excess gravitational lensing to infer the existence of invisible dark matter halos surrounding galaxies. In a refractive framework, a galaxy is a synchronized collective of mass that generates a macroscopic velocity gradient in the vacuum. The flat rotation curves observed in galaxies dictate a specific extended optical profile. This profile creates a macroscopic gradient index lens, or GRIN lens. Light follows the path of least time through this gradient, bending inward purely due to classical refraction. This refractive bending matches the excess lensing observed by modern telescopes. This optical effect occurs without the need for additional particulate matter. The data gathered by our most precise instruments, like the Planck satellite, records these structural variances with high resolution. The measurements are accurate, but attributing the signal to a new fundamental particle is a categorical error. Dark matter is not a particle. It functions as a macroscopic GRIN lens, an optical property of the collective vacuum fluid. Dark energy and dark matter have historically been treated as two distinct, unrelated problems. They are actually coupled manifestations of the same geometric phenomenon. Both arise from the single scalar potential field, phi of r, inherent to the light path. Traversing this potential longitudinally creates the illusion of accelerated expansion. Interacting with these gradients transversely creates the illusion of invisible mass. Applying the optical metric to general relativity removes the requirement for the unknown 95% of the universe. This requires a shift from viewing space as an empty grid to recognizing it as a refractive continuum. This approach relies entirely on standard Schwarzschild metrics and post-Newtonian approximations. It introduces no new particles. The universe appears materially simpler, though optically more complex. We are not looking at a direct geographic map of space, but an image viewed through a fluid-like gravitational lens. The anomalies currently challenging our models are the predictable artifacts of viewing the universe through its own gravity.